I'm going to talk about a problem that's really been on my mind a lot that actually I know you share. And I'm going to I'm going to tell you a little bit about what we've done about it, but I'm going to focus the questions on how to move forward, and that is technical for this particular group of people. It's not exactly math technical, but it's very much on point for what we're working on. So let's just get a few things straight. I'm going to talk about individuals. My individuals are like people in the real world. And then, obviously, as you know, the algorithms that we have, both for training and then in practice, only operate on representations of individuals. Somehow or other, people are mapped from real-world life to what we call representation space, and which definitely loses information. And the algorithm only knows what it is told about you. It's also quite possible that, depending on how you do this mapping, that distinct individuals could map to the same point in representation space. But in our thinking, the representations are very rich. And so there's a lot of information about you, so we're not going to assume that there are these kinds of mapping collisions. It's okay if there are, but we're not going to assume them. Okay? So, now we've been, think back to Guy's lecture and the various lectures where we're talking about some kind of reality called P star. And whatever it is we're talking about, P star is somehow or other the individualized probability of a positive outcome. We know that this is highly contentious, that there isn't necessarily agreement on this at all. We don't know how to define individual probabilities. That was the impetus behind the work on outcome indistinguishability. But, we do know that algorithms assign numbers to people, and these numbers are often interpreted as probabilities. So if we have a PI star of, say, 2/3, that means that we think that what actually happens is a draw from a probability distribution that has 2/3 probability of a positive outcome, 1/3 probability of a negative outcome. And it may be the case that there are no true probabilities, that everything is either 0 or 1, and that our perception of things as having a probability comes from a lack of sufficient information or computational power. This is a long-standing question. We are not going to resolve it. No theorem that we prove could ever resolve it. So just understand that, this is a question mark, but everything that we do is agnostic on this point. We don't actually care whether there are real probabilities or not. We don't need to resolve it. Okay, now since we're assuming no collisions, or if we have no collisions, then it's the case that a probability here for the real individual gets attached to the representation. It just gets imported along with it. It doesn't mean that from the representation you can see it, but there's a well-defined notion of what is the probability of this item in representation space, given that there are no collisions. Now, it's clear that the PI star values are contextual. Whether you're going to recover or not may involve your interaction with the physician and the technicians who are performing tests on you and things like that. It's also clear that, say, whether or not you are going to succeed in your work environment depends on your work environment. And somebody with exactly the same skills could do very well in a work environment that is supportive and do very badly in a work environment that is not supportive. So my favorite example of this is what I call nice news and nasty news. So nasty news is an environment that has sort of traditionally harassed women, and women leave. They don't stay for 2 years and get promoted. And so that's considered not succeeding. But in another organization, Nice News, where there is not a culture of harassment, the very same people could thrive. Did you have a question, Frauke? Okay. All right. So the PI values are, the P star values are contextual. We're bracketing that for now. Okay, so let's just review what we mean by calibration. So the question of individual probabilities has been studied for a long time, and early works on this. So in statistics, people said, you know, what should probabilities, what should these things be? And a very common scenario that is studied in the statistics literature is online forecasting. So every day, the forecaster pronounces the probability of rain the next day. And in early work, say in 1982, Philip David suggested calibration as kind of a sine qua non of a forecaster. And what is calibration? It says, look at, for any value v, think 0.3, 0.7, look at all of the days on which the forecaster gave a forecast of v. Then in the limit, if we look at all of those days, then in fact on a v fraction of them, there should have been a positive outcome. So on the days that the forecaster said 0.7, 70% of the time it actually rained when we look back after kind of an infinite number of steps, and similarly for 30% and so on. Now, calibration doesn't imply accuracy. So for example, suppose the weather pattern holds year after year, and the forecaster just gives, as the forecast, the kind of typical number of days of rain in the year, and repeats that same exact forecast every single day, you know, 120 out of 365 or something like that, every single day. So that's calibrated because in a given year, if you look at those days, you know, I mean, it'll be doing the right thing, but it's not very accurate. It's not very useful information. Even worse, as de Groot and Feinberg point out, it doesn't even incentivize accuracy. So suppose you are the forecaster and you're going along making predictions, and you see after some time that you've been kind of, the days where you were predicting 30% chance of rain, it really only rained on 10% of those days. So now the next day comes up that you're really, really sure it's going to rain. So what you do is you say, I'm going to assign this 30% as the probability, because that'll get your 30% numbers up. And so you will improve your calibration. So again, it doesn't even incentivize being correct. Okay. So now we're going to move to multi-calibration, but I just want to preface this with there's a general multi-X framework that arose perhaps in the following way. So before this work, which was sort of 2016, 2017, and the literature had kind of split into two kinds of fairness guarantees. One of them were simple group fairness guarantees, like we have two different groups, S and T, and the false positive rate for S is the same as the false positive rate for T. That's our group statistical guarantees. And the other version was, and for reasons that we discussed, that Guy discussed, for example, these turned out to be problematic. Like, a big reason is that natural desiderata are mutually inconsistent. The other vein had been what we call individual fairness, which says, for the given task, there is a metric which says, for this particular task, how similar or dissimilar any pair of people is. And if you had your hands on such a metric, that's a very, very powerful thing, and then you could ensure that similar people are treated similarly. But the problem is, how do you get your hands on the metric? So a lot of interesting things happened in that direction starting about 2018, 2019, but this work is kind of maybe in between. It says, well, we're going to look at groups, or pairs of groups, or sets of groups. we're going to allow them to intersect arbitrarily, large groups that intersect arbitrarily, as shown in the picture. And two different groups of researchers said, let's look at these things, and so this is the word multi, because we have multiple groups that have arbitrary intersecting patterns. And we're going to impose a fairness condition for all of these groups simultaneously. Like for all pairs, maybe we want the same false positive and false positive rates. Or in this particular case, what we're going to be focusing on is multi-calibration, which, as Guy introduced yesterday, work of Aber Johnson, Kim Reingold, and Rothbaum. Now, so what does multi-calibration say? We're actually going to picture it a few times, but you saw the calibration condition on the previous slide. So here you have some arbitrary large pre-specified collection C of sets, and the requirement is if you just look at the behavior of your predictor on any set in that collection of your choice, on every single one of them, the predictions will be calibrated. So not only are the predictions calibrated on the universe as a whole, but also on these different intersecting subgroups when looked at individually. So that's a lot more, it could be a lot more power. So the multi-X framework, X is specifying a group fairness guarantee. In this case, it will be calibration. And the multi says that the requirement applies simultaneously to sets in this pre-specified collection. So it's natural to say, why on earth is calibration a fairness condition? Calibration was proposed as a fairness condition in work by Kleinberg, Mullainathan, and Raghavan. And they were not thinking about this arbitrary intersectional whatever. They were thinking about two disjoint groups or a collection of disjoint groups. And their view of it was, if your predictor is calibrated on each of S and T, then a score of, say, 75% means the same thing whether you are in S or in T. A score of 75%, quote unquote, means that among the people who got 75%, in fact, 75% of them would be positive. So it says that the idea, I believe, was to try to cut short any reasoning about, oh, what does this score mean, given that this is a person in this group? Were the scores perturbed or whatever? No, they weren't. They mean exactly what they say they mean. That seems, if I have understood their work correctly, that seems to be the motivation. Okay. So let me just give you one more view of multi-calibration. Here I have the predictions. I've taken the space of instances, and I have the predictions of our predictor that we built, P tilde, not real life. We don't know what P star is. We don't know what nature has in store. But this is what the predictor is saying. So in the yellow region, the predictor is saying 0.1 for everybody in the yellow region. In the red region, it's saying 0.2, and so on. And now let's look at any set T in our collection of sets. T intersects these regions. So what we have, can you see my cursor? No, let me, does this work? Oh wait, let me get a cursor for the people on this pointer. Okay, so if you look at these people, they're purple people who are inside the set T, then indeed a 0.3 fraction of those people will have positive outcome. So if we look at the intersection with T, we see that P tilde is in fact calibrated on T. So this is just another visual view of what multi-calibration means. And this would hold for every set T in our collection, and these sets can intersect however they wish. Okay, so now comes the important part, the set collection C itself. So the first question is, which sets should be in C? And I claim that this is a ubiquitous problem that shows up in lots and lots of places. So for example, you might be generating synthetic data Maybe you're generating synthetic data for reasons of privacy. You don't want to release real data. And you want to ensure that the statistics that you compute on your synthetic data look much like the statistics that you would have computed on your real data. We're going to allow some difference for the purposes of privacy, but it's important that you have to specify up front, what is it? What queries are you going to try to promise to answer accurately? You need that information for building the synthetic data set. And if you don't do it, and you end up with a blob of some sort, a synthetic data set, let's say, that allows you to have very accurate answers of too many different queries, then you will violate what we talked about the other night of the fundamental law of information reconstruction. So it is important to decide a priori what is it you want to be preserving. The same thing happens when you try to build any kind of modeling something or other. You have to decide what is it that you want your model to preserve, predict, give people. So it's not really a new question, it's just showing up in a new form. Now, my concern, and what really woke me up about multi-calibration, is completely separately. I had been thinking about the problem of, in general, when you're trying to ensure fairness with respect to groups, which groups should you list? And the issue for me was there are going to be groups I haven't thought of. Try as I might, and reading the newspapers and trying to be as informed as I can be, I'm certainly going to miss some. And who in 2010 was in the algorithmic fairness community was thinking about, say, the set of non-binary individuals. For many of us, unfortunately, it had barely entered our lexicon, and it wasn't kind of front and center in the thinking. Or let's take a new collection, a new set of people who are going to be at disadvantage, women who will grow up without access to safe abortion, new in the United States. That wasn't in the set collection that anybody was listing in the United States in 2010. So how do we sort of think outside the box and make sure that we're listing the right collection of sets for whatever our fairness requirement is? And some of the things that I thought about was, well, whose job it is to answer this question. So do we expect the FANG companies to do this? Is it in their interest to do this? Is it appropriate to place the onus on the members of these groups who would then need energy and time and just general wherewithal of the knowledge of the salience of their trait to stand up and say this is a set that should be included in the collection? And in fact, I was also concerned with what's called system justification. So this is the justification is an idea that's being used to provide legitimacy or support for another idea or for some form of behavior. So people generate beliefs, they generate beliefs about themselves in response to the way they are treated. And trying to reduce perhaps a cognitive dissonance between how they think about themselves and the situations in which they find themselves. And if you push that, you can see that a group simply may not actually have the self-awareness because of this situation to advocate for themselves. Okay, so what I loved about the idea of multi-calibration was that you could specify the collection of sets with a class of functions that is based on the computational complexity of the function, the set membership. You know, maybe things that you could compute with small circuits or small decision trees, something like that. So in some sense, by offloading the responsibility onto the job of just being captured by a complexity class, you no longer have to make a list. You just say, here, this complexity class. So that was amazing. You know, complexity theory rocks. It was a great idea. It is a great idea. We do need that membership in the sets is identifiable in the base class C of computations. We're going to bracket that for now. So you know, everything was great and happy. And then we started thinking about computational costs. So if you have a large and unstructured set collection, you know, how can you ensure that you will be calibrated on all of the sets in this collection? And that turns out to be prohibitively or unaffordable. So it's affordable when the set collection is small or has some nice structure, large but has some nice structure, something that permits something called weak agnostic learning. And there are heuristics for this, but we don't necessarily want to, I mean, just flag this, it's like, for really unstructured sets, there's no help. And so, in some sense, I was back where I started in that this was exactly what I hoped to avoid. I didn't want to have to start intelligently listing a small collection of sets or intelligently finding well-structured collections of sets. So the next question is there any alternative to actually listing the sets? You know, we've been talking about this pre-specified collection of sets. Is there any alternative to it? Well, accuracy is a runaround this, in the sense of if you're accurate, you're automatically going to be calibrated on large sets. So that would be one way. So here's a question before we pursue that one. Does multi-calibration with respect to a large collection of sets imply accuracy? So we know that just calibration doesn't imply accuracy. We gave examples where the forecaster is giving the average probability of rain over sort of all days. So what about if we have a big set collection and we're calibrated on each of these sets? Is it better? Not necessarily. So here's a first example. Suppose every set in our collection is just some large or not necessarily large, I don't know, random sample that's chosen completely without regard to P star. You just randomly subsample. What can we say about the people in our random subset? They're the ones in red in this picture. What can we say about them? If we look at them as a group, their average P star value is very likely to be very close to the average P star value for the whole population. Why? Because the field of statistics works. It relies on statistics, relies on the fact that a random sample that's large enough is very likely to have nearly the same average as the population as a whole. This is how we estimate means. We take a collection and we look at it. Okay. Here's another example. In her work, Talent is Everywhere, Danielle Allen, in 2014, was proposing a particular method of choosing students for university. But her point is, talent is kind of uniformly distributed around the country, so we should break things up by zip code. Zip code is not related to talent. Okay. At least in some way. Okay. So multi-calibration with respect to kind of the wrong collection of sets C does not guarantee accuracy. Now, the truth, which we're calling P star, and of course, again, in many cases it will be contextual and about the relationship between the individual and the environment, but we're bracketing that as well for now. The truth may be very complex. As Guy pointed out, it may be much too complex to express with the given set collection, even if this set collection is very rich. So the question we ask is, well, what if the truth is not all that complex or is not all that hard to approximate? So let's talk about this a bit. What's the philosophy in AI? What's the philosophy in, say, training big neural nets? So I went out and I read about this a bit, and a lot of the discussions will say, well, we train neural nets because we think they might be able to approximate the thing that we're interested in. That's why we work with neural nets in the first place. If we thought they were going to be hopeless at predicting what we're interested in, we wouldn't be using them. So we use them because we think they're going to be useful. So this may be debatable, but let's go with it. Now, with that philosophy, your basic objects of interest are useful. They're very useful. It's very different than, say, in cryptography and complexity. So, for example, pseudo-random strings are very different from truly random ones, like there are fewer of them. But under standard complexity theoretic assumptions, we don't have a way to efficiently test or audit or distinguish the pseudo-random ones from the truly random ones. So, somehow, it feels to me as if in the AI world, we're saying, yeah, we can do everything. And in the CS world, we're saying, well, we can't do everything, but what we're doing is indistinguishable from everything. Okay. Going back, digging in further to the roles of the sets in multi-calibration, the sets play two roles. One of them is the listing of demographic groups. This is where the fairness is coming from. And the other is stratification or differentiation, so that somehow they're separating out the high P star instances from the low P star instances. So in order to get any accuracy from multi-calibration, we need good sets. We need good sets to get non-trivial utility. So we have to assume that our base computational objects really can do something that's related to the task of approximating P star. If definitions of the sets were independent of P star, it would be hopeless. We saw that already. So, for fairness and accuracy, ask me about this if there's time in the Q&A, because I'm running a little short on time. But basically, all of this work is describing the world as it is and not where we want the world to be. And as far as we can tell, both fairness and accuracy appear to depend on the richness of the collection C as sets. And the construction costs can be prohibitive when C is rich. And that brings us to this question which we call the scaffolding sets. Can we efficiently find a small but mighty collection of sets C? So by mighty, I mean that if we multi-calibrate with respect to this small collection, we're going to get a good approximation to P star. So as a thought experiment, suppose somehow we had our hands on the level sets of P star. That is, we had our hands on a set where everybody in the set has a P star value of 0.3, and everybody in this set has a P star value of 0.5, and so on. If we had our hands on those, then if we calibrate with respect to those, we would automatically get accuracy. And if we have accuracy everywhere, we get calibration for all sets. And more generally, if we have any collection of sort of mono-valued sets, like these, but maybe there are two sets that have P star equal to 0.3, any collection of that covered the universe, we're fine. So that gives us the scaffolding set problem, which is, can we efficiently find a modest-sized collection C of sets such that multi-calibration with respect to C yields a good approximation of P star? And what we found was that, yeah, in some non-trivial and interesting cases, we can. So sometimes we actually can do this. Can we know whether we've succeeded? Absolutely not, because if we did, we might actually resolve the question of whether there were integer or non-integer, whether there existed non-integer probabilities. So no, we can't know when we've succeeded. So what do you do with something where sometimes it works and you can't tell whether you've succeeded? What you want to do is you want to use it, and if you have to rely on it, that's the best maybe the best you can manage, but typically you won't have to rely on it. So suppose you were planning to try to do multi-calibration with respect to your favorite class of sets. We would say, find a scaffolding set collection, calibrate with respect to these, which might in fact be giving you accuracy, and now go and do whatever else it is you want to do, calibrating with respect to other sets. Any way you can, anything you can manage computationally, knock yourself out, but do it as post-processing. One of the important points that Guy made is that the multi-calibration algorithms don't hurt accuracy. So if you start with something that's accurate and then you post-process it, or you don't make the accuracy deteriorate by the post-processing. So, yeah. Okay, and just to give you the slightest bit of intuition where this comes from, there's a folklore that says the intermediate layers in a neural net may provide a high-quality representation of the input. And there's a fair amount of literature that looks at low-dimensional intermediate layers. And so when reality can be approximated by some kind of nice dimension reduction, followed by a suffix that is well-behaved, and technically it has some nice Lipschitz guarantees, then when reality can be approximated this way and the data come from a sufficiently nice distribution, then it works. So examples would include single index models and transfer learning situations. If you're not familiar with transfer learning, think about the intuition that if you have learned Italian, then solving the related task of learning French is easy. And there are two different realms in which people do this. One is where they assume that the relationship between X and its label 0, 1 is the same, but you have different distributions on individuals for your different tasks. And the other is concept shift, where the relationship between X and Y actually changes. And in both cases, you need some kind of diversity conditions, either on the marginal distributions or on the conditional distributions to make things work. So, almost done. Why not just learn P star? Why go through this, dimension reduction, blah, 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 blah? And there's some answers. First of all, it's sufficient to learn the dimension reducing mapping. Sometimes that can be easier than learning P star. In particular, in the transfer learning setting, all your different tasks would share the same dimension reducer, and so you get a lot of data for that, even though for any individual task, you may not have such plentiful data. And the function that you construct may not be computable from the base class that you're working with. So it's another reason to go through this procedure. This was my last slide. Going back to our original question of which sets, we saw that it was a ubiquitous problem. That it's important to do something automatic, maybe, that lets us think outside the box. Now, but let's not think outside the box for a minute. Like, which sets do we really have to include? So channeling Deborah Hellman in her book, When is Discrimination Wrong? And the answer is when it demeans, which involves piling on previous discrimination or previous wrongs. maybe we could say that it's at least only or at least most relevant for historically mistreated groups. And that would say that you only need to worry about the images under the representation mapping of sets that are easily recognized by humans. And that may cut things down quite a bit. Now, you might or might not believe this because, of course, if we build a predictor and it's unfair to a certain group, I don't care what this group is. It may be people who like to wear green shirts. And then it ends up being used really, really, really widely, then you start creating discrimination against people who wear green shirts. A concept which has more recently been written about as the algorithmic Leviathan by Creel and Hellman. So I want to end with a question. We've been very concerned, correctly, about incoherent categories, especially, say, race when used in a medical context. Or we talked about cases where sex is actually an incoherent concept. Now, sort of knowing how multi-calibration works, it's not clear to me that the incoherent categories is harmful in this setting. I don't know, but I think that this is something that we should look at and resolve. It should be resolvable, but my gut is telling me that the way the multi-calibration algorithms work, every time you have an update to your algorithm, you're always marching closer and closer to P star, and you're hopefully, you're not regressing too much. So I don't know, but I think it's worth looking at. And that's it. Thank you.